Thank you, Miguel, and thank you for this opportunity as well. So, before I start, I would like to thank to acknowledge the co-authors on this paper, on this presentation. Many students from my group, as Ben was mentioning before, this wouldn't be possible for any of us without very good students. So what I want to do before is I would like to know how many people have worked or work in combustion? Okay. Not zero. This is good. So what I will try to show today is some techniques that we have been using to for reduced order modeling in combustion. I will explain why. I hope that you see ways that these techniques can be useful to you, and so I would be interested, in the end, to see this kind of feedback from your side. But I am interested in applying these approaches to problems that I've seen this week. So to start, we have discussed about the place that machine learning is taking in our work and in our approaches today. And you're probably familiar with this sketch of the scientific method. We go through reality, the definition of conceptual model and computer models. And what I really think is the key for using machine learning in the future and to make the best use of machine learning in the future is that of bringing it inside the scientific method circle, which means coupling machine learning with computer models, embodying in machine learning tools all the a priori information that we have about problem physics, and improve these machine learning tools based on the feedback that we have from validation experiments. But the other very important question that we have to ask is what are we after? And I think this is a very critical point, and it was pointed out by Professor Brunton in the morning. So we have to define the questions that we want to answer. And based on these questions and our intended use, our objective, we will define the approaches that we have to use. It was mentioned that machine learning is not neural networks. It's true that most of the time you will be better off with approaches that are different than neural networks. Okay, so this is something that it's really important, and I wanted to point it out. Also, you're probably familiar with this quote from the statistician George Box. So all models are wrong, but some are useful. Professor Jimenez, that I don't see here, also taught us on Monday that the data will tell us if the models are wrong. But I would add something to this sentence. I would say that the data will tell you if the models are wrong, given the intended use of the model that you have in your, the objective that you have for your model. And this is very important because there isn't a best model. There is a model that is useful for your application. And I think that this is really interesting to see the use of machine learning and data in building the generation of models. I think a way that we should see the development of this model is in hybrid models which couple physics-based information with the exploitation of data in several different ways. And we have seen that there are many important, very, very interesting algorithms to do so. And this is really important to go towards very complex problems that could be multi-physics, multi-scale simulations, or digital twins for control and sensing closures. This is a big problem in many applications. Okay, so let's move on. This doesn't work. Okay, so why is data-driven modeling interesting for combustion? So for the people who are interested in combustion and no combustion, maybe this is trivial, but I would like to motivate why this is interesting. So combustion is intrinsically multi-scale and multi-physics. You know that it combines heat transfer, chemical kinetics, fluid dynamics. Moreover, if you look at chemical kinetics, this scales 12 decades of scales, which can be more or less coupled with the fluid dynamic ones. So you see that you have a very complex model, process Because if you have to take both of them into account, then it becomes very complex to do so. We have a curse of dimensionality in the sense that we have very large dimensionality of the state space. Chemical kinetics for standard fuels involve hundreds of species and thousands of chemical reactions that are tightly coupled in kinetic mechanisms. And then you have, on top of the nonlinearity of turbulence, you have nonlinear turbulence chemistry interactions, and the evolution of the state space is highly nonlinear because mainly of the Arrhenius kinetics. Okay, so you see that you have a number of challenges that make the use of machine learning, data-driven modeling, reduced order modeling very appealing for these applications. So to show you a little bit what this multi-scale, multi-physics challenge is, you see here the 12 decades that chemistry can span, and here are the fluid dynamic ones. And so based on the overlap or not of the two processes, you might have combustion process which are slow chemistry, finite rate chemistry, or fast chemistry. And we denote them by using a number which is called Dunn-Keuler number. And so if the Dunn-Keuler number is very fast, is very large, sorry, it means that your chemistry is not the limiting process, it's a very fast chemistry. If it's very small, you are in a slow chemistry kind of regime. It's otherwise, you are in a finite rate regime. So guess most of the time in which regime we are. In the finite rate, and so it means that we don't have any chance. We have to take both of them into account. Okay, so because of course, if you were here or there, it would be easy. We can decouple the two phenomena, but we can't because we are in the middle. Okay, and then this was the second issue. It's the dimensionality. So you see it very clearly here. You see that the number of species in a kinetics mechanism increases very strongly with the number of carbon atoms, and unfortunately, the CPU time also increases with the number of species, but with the power of 2.5. So you see that this makes the whole problem really challenging. Okay. Now, in combustion, there has been an increasing interest in the use of data-driven approaches. I made this search very recently, and if you make it a 10 years span, you see that there is a very strong increase in the use in the papers that actually report either machine learning, feature extraction, data mining, and combustion. So this actually shows that there is a momentum in using this, and this is clearly motivated by the three reasons that I showed before. Okay, so what is the two things that I will talk about, and what are, in general, the things that are interesting in our community. So there is a lot of data interpretation and feature extraction. I will talk a lot about that. And this is important because we want to identify low-dimensional manifolds in turbulent reacting system, meaning we want to find a compression, optimal compression for our state space to reduce the number of variables that we have to account for. And then the second one is that we want to reveal key features of new combustion modes that are interesting, for instance, because they are less polluting, but they are very, very complex. And so the use of high fidelity simulation and data mining approach can help us in this respect. And then, of course, we want to predict stuff. And so we want to develop new closures. We want to replace or couple a data-driven approach with the physics-based one. Or we want to develop reduced order models for uncertainty quantification, optimization, like digital twins. And so I will talk about digital twins in the end of my presentation. Okay, so many tools for feature extraction. Some of them, many of them have been mentioned in this during this week. So PCA or POD, nonlinear principal component analysis, isometric mapping. Do you know anyone has used ISOMAP? Do you know what it is? Okay, TSNE. Autoencoders, yeah, I think many of you. Okay, and I will talk in particular about a technique that we have developed, contributed to develop. It's called local POD or PCA, and it shares some similarities with the clustering approach that Professor Noack was mentioning before. Okay, so I don't want to go, so I will not have equations, but I just want to say how we assemble our matrices if you'll be using our codes. So we have a state space that consists of temperature, pressure, compositions, okay? So we assemble the data in this way. We have each row is an observation, and then each column would be a different state variable. And then I can skip this very easily. You have had all the introduction to PCA. Then we call, you will see that I mention some things that are called principal component scores. These are the projection onto the eigenvector matrix. We have a scaling matrix because our data are scaled, and I will come to that in a moment, since we have different units and different scales in chemical species. And we also center our data, as was pointed out before in the presentation of Professor Nowak, okay? And so you have a centering matrix, scaling matrix, and eigenvector matrix. And so we have, we talk about principal component, truncated principal component scores, and a low rank approximation of our initial matrix X of data. Something else I want to point out, why we center just as was mentioned before, because we have to convert observation to fluctuations. And we also scale because in our problems we have temperature, we have stable species of combustion, we have radical species. So they span scales which are very different. And so to take all of them into account, we have to scale appropriately the matrix. And so I don't have time to go into the details of that, but this is a tutorial that we have written with Einspeech at Aachen. And so if you are interested, you can look it up. And something else that we do, it was mentioned today, again, I will not go into the details of that in this presentation, but we also pre-process data. We use principal component classifiers as approximation of the Mahalanobis distance to see from the empirical distribution of the data, what are the outliers in the data. And so this is very important when you have experimental data. And so we have in our field a lot of experimental data coming from the San Diego National Labs or many other labs in the world. And so it's really, really important to detect both the univariate and multivariate outliers that you might have in a data set. Okay. This is just for you. This will be uploaded afterwards. So if you're interested, you can go and look at all these references if you're interested in looking at those. But so, as I was mentioning before, PCA and other approaches have been applied to a large number of experimental and numerical data sets. Numerical data sets are increasing every day. So you have DNS data that are generated maybe as we talk. And here you see some of the references that I have collected, but basically this is this is not a problem anymore. It's probably the opposite. We have a booming of data, and so we will have an increasing availability of data in the future. But you see, you have simple flames. This is a simple jet flame. This is a piloted flame. This is a lifted off flame, and this is a diluted flame, and then you have different configurations, flame vortex interactions, premixed flames, and so all sorts of things that you can imagine. Now, when you do PCA, of course, you do this eigenvalue decomposition. You find the principal components that will explain a certain amount of variance that you want in your data, and then you get this best multilinear approximation of your data. So it's multilinear because you have different linear contributions. And of course, I mean, you have this approximation, but you know that most of the time, especially in combustion, your data present no linear features and no linear interactions. So the fact that you're using a multilinear approach might be problematic because you might actually find additional dimensions just to make up for the nonlinearity of the manifold. Okay? And so this is important because this explains why people in combustion have looked into other approaches to perform PCA. And so one of them, for instance, is kernel PCA. And so the idea is very simple. You perform a PCA in a feature space where the relationships are linear. So very similar to what was mentioned for POD. The problem is that the computation of this kernel can be very expensive and can become unmanageable for large data sets. So this has been used, but on very small data sets, and not DNS-like data sets, because of this problem of dimension. And you see here it was applied on a one-dimensional turbulence approach. So it's the equivalent of the linear eddy model. Anyone familiar with that? It's a one-dimensional turbulence simulation where the three-dimensional mapping is built using a statistical approach. Okay? And then you see isomap, isometric mapping. Anyone has used it? So this is also another approach which is very similar to kernel PCA, but here the difference is that the kernel is the geodesic distance between the points. And so this is very interesting because you know that Euclidean distances may not be the correct metric in high-dimensional spaces. And so the idea here is that you keep the distance between points the same in the original and in low-dimensional manifold. And you see here an application from the group of Jackie Chen at Sandia. You see here a DNS of DME combustion. You see here an interpolation in space, and then on the left and on the right side, a 2D, a three-dimensional LDM application. The other problem here is that you have to build a graph to find the shortest path between 2 points. And so this path search can be very, very expensive. And so this is also why this approach is limited in use for data sets which are very, very large, like in combustion. Other approaches which are similar to that, it's the TSNE, so it's the T-distributed stochastic neighbor embedding. So it's very similar to the isomap, but it's a probabilistic version of that. So you have points which are close to each other, and you want to be sure by minimizing the likelihood that the probability that two close points are close in the original space, they will be also close in the final space. Okay. Now you see that this has very nice features because here you are looking at 13 different premixed flames, and you see that the approach is able to set them apart one by one. So it has very nice feature of putting these feature of the different features of the database apart. The problem, like in many neural network approaches, I think, I mean, this is at least my point of view, is that you have many hyperparameters to tune to get these results. And sometimes it can be very messy, and you don't know why, and then you have to do trial and error and so on. And then autoencoders. Autoencoders have been presented today, so we have applied also them on combustion data. You also know that if you have a very shallow with the linear activation functions, you have nothing but the principal component analysis, or PRD. But here the idea was to compare these autoencoders to locally linear PCA approach. Okay, and so we applied that to a DNS jet. So you see here the original temperature field. This consists of 12 state space variables. The grid points are about 2.5 million per time step. And you see here the autoencoder reconstruction. You just see the reconstruction of the relative error with 4 layers. So it's not a shallow network, and 2 components only. So from 12 to 2. So you see that it's pretty okay. You have some regions where you have some error, but still it appears to be quite reasonable. Okay. Now, why don't we look at approaches that are based on PCA? So what we have seen here is that the limitations of PCA have prompted let's say the development of approaches which are based on nonlinear search into let's say nonlinear data set to parameterize these nonlinear manifolds with fewer dimensions. The problem with these approaches is that they can become computationally intractable, and this is the point. This is, for instance, the case for kernel PCA or isometric mapping, or they can involve a large number of hyperparameters. And this is, I think, personally the case of both approaches like TSNE and autoencoders. And the other observation that I also make is that when you use these nonlinear approaches, you get features that are very difficult to interpret. If you try to interpret autoencoders' codes, then you have to use correlation analysis. You have to see which are the variables in the state space which are mostly correlated to the codes. So it becomes quite difficult to get a clear understanding of what is going on. So this actually prompted us to look into linear formulations of PCA. So imagine you have this nonlinear manifold. You have a multidimensional point. So what you can actually do is to imagine to do a piecewise linear PCA reconstruction by minimizing what? The reconstruction error of each point to the one of the four directions in this case. And of course, this can be generalized to any number of clusters and or to prescribe a predefined reconstruction error. And the idea is that you get, in the end, an optimal decomposition of your system into different regions, a little bit like was presented by Bernd before.
But why can't you use locally linear embedding? Just something very, very similar.
Yeah, maybe it's very similar, but what we, I'm not sure that in that approach we can actually prescribe, because what we do is that, you will see in a moment, we perform iterative algorithms that minimize a cost function that we define. Okay? And so we can define the cost function to suit our purposes in other means. Okay? So now imagine that you have this original field from the DNS. In this case, we are not looking at temperature now. We are looking at the OH radical. Okay? And you see that it's here you have the fuel region, on the sides you have the air, and then you have a very thin layer of OH. Now, if you try to apply global PCA to get this field, you need at least 5 eigenvalues, and you still get, a decent approximation, but it's not perfect. While with the local PCA, a certain number of clusters and 2 eigenvalues, you get a perfect reconstruction. This is actually more visible when you look at the parity plots. So you see here that you still have an error which is above 14%. Now, when you compare these two autoencoders, it's also remarkable that you are able to get with local PCA results that are better than what you would get with the same dimensionality of an autoencoder. Now, I want to be very clear here. I'm not saying that, so autoencoders, neural networks are universal function approximator. So it means that there should be a setting of the autoencoder that will give results which are better than local PCA. But the number of hyperparameters that you have to train and to optimize to get this result become very large. And so at a certain point, it's not even interesting to do so. This is at least what we have observed in our work. So you see here the reconstruction error for the different variables. This is the DNS flame of reference. And so you see the results obtained with the different approaches, PCA, local PCA, and the the different autoencoders. And you see here this very clearly. You see the global PCA results. These are all relative error on temperature. You see very clearly how these performances of local PCA are improved, and also on the reconstruction of very small radical species. So a radical species is in combustion a species that wants to react because it has an unpaired valence. And so it's not stable, it will react to form either another radical or a final product, okay? So you see here that also these minor species get really, really well with this approach. Now, of course, someone could say, but in your approach you also have hyperparameters, right? Do you think that I have in local PCA hyperparameters to tune? Yeah, but I have only 2 of them. I have the number of clusters and the number of principal components.
And your metric.
And the metric, okay? But the metric is the reconstruction error, okay? Okay, now, before we move forward, I have to introduce a variable, because otherwise nothing that I say will be clearer. So I have to introduce a variable that is very important in combustion. It's called mixture fraction. And this is the ratio of the mass of mixture leaving in the fuel side compared to the mass of mixture in the control volume. Basically, the mixture fraction will tell you how much fuel you have locally inside your domain. So it's a measure of the stoichiometry of the system. Why this is a so important variable in combustion? You see it here. When I plot temperature as a function of the mixture fraction, I have this kind of behavior. You see that you have a maximum. This is where I have a stoichiometric condition, more or less. But something which is remarkable is that most of the nonlinearity in the data is captured by this variable. Okay? So you see that you have this nonlinear behavior, and this nonlinear behavior is mostly captured by mixture fraction. Of course, you have a simpler data set where almost temperature is only one function of mixture fraction, but then you have very complex ones when the mixture fraction alone cannot explain everything in your system. You see that here you have a scatter. In this condition here, I can have points which are ignited, non-ignited, and so on. And it means that I still have most of the nonlinearity in the mixture fraction, but I also need other variables to explain my process. Okay, so this mixture fraction will be used in the following as a variable that best parameterizes combustion systems. Okay, now this is important because I want to talk a little bit about the two algorithms that you could use for doing this local PCA in combustion data. And of course, you might think also at applications in your cases. One of them is that I do this completely unsupervised. And I have to use, let's say, an approach or a metric to define how iteratively I converge to a certain cluster separation. Okay, so what we do is that we initialize centroids randomly or uniformly in mixture fraction space or from k-means. This is our initialization. And then we partition into the clusters, and we build this reconstruction error. So we are looking at, for a given dimensionality or number of eigenvectors, we see what is the error between the original data and the projected one. And then we iterate to minimize this distance. So what will happen is that the data will be assigned to clusters that minimize the reconstruction error. So you will have an optimal reconstruction of your data into clusters. Of course, you could say, okay, you know that mixture fraction is a good variable. Why don't you cluster on mixture fraction? We said before, this mixture fraction has most of the nonlinearity in the data. One possible option is to say, okay, I split into bins on mixture fraction. This is my ideal clustering. Problem is that this is not always ideal. As you saw before, for data like this, you don't know if working into these bins of mixture fraction is optimal or not. So to give you an example, looking at the same data set I had before, if you do a mixture fraction partitioning, so a supervised partitioning of this data, what you get is simply that I'm splitting the data into the rich side, so the air side, and the fuel side. But if I ask VQPCA to extract or find two clusters, you see that it's very clever because it will extract the reacting layer from the non-reacting one. So it's really getting an important feature of my flame. But then this was my presentation before I saw Professor Jimenez's talk on Monday, and he was saying, are you really sure that you're getting a good feature? How can you say that you're getting a good feature? So this is, then I went back home and I called all my PhD students, and then we sat together, and basically we decided to make a test to see if on manifolds that we know, we could prove that we were extracting the good features, okay? And so we did that. We took two manifolds which are famous in combustion. One is the Burke-Schumann, and one is the equilibrium manifold. Why they are interesting? Because in this manifold, we know exactly the state space. I mean, we know what the state space is function of. We know that these are both state spaces which are only function of the mixture fraction. And so you see that, for instance, for the Burke-Schumann, this is a case of a very high uncolored number, one global reaction, first law analysis, so no equilibrium involved. And so you see that you have piecewise linear relationship for the temperature and also for the species. In the equilibrium manifold, we use the first and second law analysis, and we minimize the Gibbs free energy of formation. And this is how we get it. And so these are the two manifolds that we get. You see that in one case, it's a piecewise linear function of Z. In this case, it's more complicated because it also involves dissociation reactions and so on. Now, if VQPCA is really a good feature extraction method, what do you expect when you apply it to this manifold? What do you think?